Have you ever seen a little kid put their shoes on the wrong feet before? Well, it doesn't really work that well because your left foot doesn't fit in your right shoe and your right foot doesn't fit in your left shoe. Biology has their own version of left-footed and right-footed shoes called enantiomers. In biology, enantiomers are molecules which are mirror images of each other. They look alike, but they are not the same. An example of an enantiomer is lactic acid left and lactic acid right. When flipped over a line of symmetry, they are the exact same molecule, but in reality, once they are created differently, they are never going to be the same molecule because no matter how much you rotate them, they never, ever quite look the exact same. For some molecules, if they were to be flipped over a line of symmetry, they would look the exact same. Take CO2, for example. No matter how much you flip this, it's always going to be CO2. There's not really any differences. So, back to S lactic acid and right lactic acid. No matter how much you rotate right lactic acid, it will never quite look like left lactic acid. And this is kind of the same idea as in the fact that when I put my right shoe on, it doesn't really fit on my left foot quite right. So our lactic acid can't do the exact same job that S-lactic acid can do because they're still slightly different. And these molecules that are mirror images of each other but aren't quite the same and can't serve the same purposes are called chiral molecules. So I explained what homochirality was, and the differences. I gave the example of lactic acid and the differences between them. So theoretically, if molecules were to evolve together under, Earth's early environment, they should be 50-50, righty and lefty. That's how they should evolve. But in reality, most of our amino acids are lefties and most of our sugars are righties. And in a lot of macromolecules, we find this skew. And this is kind of what sparked the realization that something had to affect this from scientists. And that's where all of the research on circularly polarized light comes from, is this idea that this doesn't necessarily line up and make sense. And scientists wanted to figure out what factor in the universe affected this. So now that we've discussed what homochiral molecules are, now the rest of the video is going to be focused on explaining why this skew of the chirality of molecules on Earth is occurring. We're going to go through the theory of circularly polarizing light and how that affects homochirality, but first we're going to go through some background knowledge. So the first thing that we'll be looking at is the miller-urey experiment. Alright, so now we're going to be discussing the miller-urey experiment, which was also known as the primordial soup experiment, and it kind of just showed that biotic things can possibly come from abiotic things, as Miller and Urey mocked up kind of the original environment that Earth was in and showed that macromolecules, which are the building blocks of life, could come out of this. So the way they set up this experiment is they had water, CO2, methane, hydrogen gas, some of the gases that were in our early atmosphere, a shock of electricity, which is also a characteristic of our early atmosphere, and water was running through the system. So the water would run through the system, it would get heated, it would evaporate into water vapor, it would come down and it would be mixed with all these gases, it would get shocked with the electricity, and then it would come down and condense. And then they took a sample here after the interaction with these gases and the electricity. And in this sample, they found some of the macromolecules that are found in our human body, and it just kind of showed that these things that we find in most life forms can come from things that, aren't necessarily living. And some of these amino acids came out of this experiment, like glycine and alanine, which are shown here. And the idea is that theoretically this experiment should come with 50-50 chirality. These molecules are under the same exact confines, they have the same gases at their subjected to, they should come out 50-50 heterochirality. But in reality, in our world, most of our amino acids, are lefties, and most of our sugars are righties. And this is kind of what first started that kind of puzzling and unsolved homochirality issue for scientists. So now that we've looked at the miller-urey experiment, and now that we have the idea that that should theoretically come out as 50-50 homochiral, and that it's not, we're going to now look at circularly polarized light and how it may affect the chirality of these molecules. And this is an abiotic factor. So before we get into the abiotic factor that ended up giving our life some confines to be created under, we're going to look at some abiotic factors and some biotic factors that affect us in evolution in general, and will help you connect the idea of how homochiral molecules were affected to how populations today and in the closer past were affected by abiotic and biotic factors. So before I get into what factors actually affected homochirality, which is the circularly polarized light, which scientists believe affected the homochirality, I want to go over some kind of evolutionary factors that have effect on populations. So even though, chiral molecules aren't living things on their own, they are part of living things, and they were affected by something that was abiotic that caused the skew of chirality. And I kind of want to go over some evolutionary factors just to connect the two, because we're very familiar with how populations are affected by these things, and we can kind of connect this relationship to how circularly polarized light may actually affect homochirality of molecules. So here we have biotic factors that could possibly affect evolution. And an example of one of these is a random mutation that's favored by the environment. And all mutations and all changes and adaptations come from random mutations, and then that individual, survives better than the others and has more offspring who are more fit than others, and that's how a mutation or an adaptation kind of makes its way into the population, and that will change how the population is. Some abiotic factors include mass extinction, so getting rid of a species might throw off an ecosystem, etc. And then the bottleneck effect, which is when kind of the makeup of the population is kind of changed because you're cutting off a certain part kind of randomly. So the individuals in that kind of random group could be very different from the original makeup of the population. Now, circularly polarized light affected how the molecules on our Earth, were developed and put together, and it caused this skew. And this factor changed how our populations then evolved. And I think that this connection between, what we know about evolution, what we know about homochirality, and how circularly polarized light might affect it, I think that connection is very important. First, before we get into why this occurs, here's a brief sped-up timeline of the universe. So here is my fancy schmancy universe timeline, and I'm hoping that it will give you guys an idea of the time period I'm talking about when homochiral molecules became affected by what I will be explaining later in the video. So 13.7 billion years ago, our universe was created with the Big Bang, and after that, a period of continuous cooling began. A few million years ago, after the Big Bang, matter began to clump together and form masses in the universe. A few billion years after that, rapid expansion of the universe continued, and that process is still going on today. 4.5 billion years ago, our solar system began to form. We began to see the planets that we see today. And then 3.7 to 4.2 billion years ago, our first organisms appeared on our Earth, which were single-celled prokaryotes. And then 200,000 years ago, humans appeared on our planet. So homochirality molecules, which is a fancy way of saying a group of molecules that are righty or lefty, must have been impacted somewhere before or during the formation of our Earth, before those single-celled organisms came about. So that this time frame in here is kind of what we're dealing with when the circularly polarizing light is going to be affecting this skew of righty and lefty molecules on our planet. So now that we've gone through a brief timeline of the universe, we're now going to talk about circularly polarized light, what it is, and how it may affect homochirality. So, there is a theory that scientists have on why certain molecules, like amino acids, are lefties, and certain molecules, like sugars, are righties. The idea is that the universe has bands of areas that are exposed to circularly polarizing light, and these areas end up having a skew in the homochirality of their molecules. And the idea is that all of the meteors and asteroids that came together to form Earth, and all of the matter that clumped together to form our Earth, was pre-exposed to some of these wavelengths of light, and that this may have possibly caused a skew in the homochirality of the molecules on our planet. So we discussed how, circularly polarized light, which is a factor that is way beyond our Earth, and these bands of the CP waves are in our galaxy and our universe, and they affect how a lot of things have developed. And this is very out of our control, but it has completely altered the way our life and the lives of all the organisms on our planet have evolved. It's put constraints on them, which is something I'm going to talk about in kind of like the ending note of the video. But this is kind of an example of how this, homochirality really does affect how things are developed in our world. So here I have kind of, not a specific example, but kind of a demonstration of the theory behind why, homochirality and, why the differences in these mirrored molecules are actually kind of important to how things work. So for the sake of this, we have molecule 1 and 2, and these are mirror images of each other that are just, flipped over the symmetrical line, and you can see that molecule 2 does not fit into the enzyme that molecule 1 fits into, and molecule 2 cannot be rotated to fit into this. So it's an inactive version of molecule 1. It's made of the same things, it goes through a very similar process to be created, but it doesn't work the same. And this is very important because this makes it so that there's more differentiation in life, so there's going to be more types of molecules, but there's also going to be these new forms of active and inactive molecules that can do certain jobs. And this, this gives a constraint on what things can do and where things go, and it does affect how our populations have evolved and how things work on the molecular level in a cell. So what I would like you to get from this video, beyond the fact that homochirality could have possibly been caused by circularly polarized light, is just simply the fact that life on Earth was created under confinements and constraints that we were unaware of for a really long time, and that were completely out of our hands before life was formed on Earth. And this idea just simply shows us the incredible possibilities the universe has, and all of the incredible life forms and things that we can't even imagine that could be out there. I think that's really cool.